Okay, now I want to talk about a tool that we use to analyze the worst case behavior of the append method and other methods that we're going to implement. It's a little weird because usually it's pretty fast. Usually it would be a constant time operation. All we do is these two things. Number one, assign a new element. Number two, remember that we have one more element. But every once in a while, we have to do a ton of work. We actually have to make an entirely new array, copy everything over, and all that. So it's like sometimes your appliances in your house break and you got to pay a lot of money. But most days out of the year, everything's working fine. So you kind of could ask the question, okay, well, I know I'm going to have some bad days, but how much do I really have to pay on average? So that's what it is. So the amortized cost is the amount of operations that you perform for a particular method call on average, all right? So in particular, the formal definition is simply amortized cost is the number of operations that you've done over the number of calls, okay? So I'm gonna focus in on just the append method for now. So let me have two different instance variables here I'll keep track of. So one, I'll keep track of the number of operations. So number of operations I've done. And then I'll also keep track of the number of calls. So number of method calls to append. And also I'm going to implement pop, another method in a moment. But for now we just have append. Okay. So it's just the number of operations over the number of calls, or in other words, the average cost per operation. Where I consider the cost to be, the average cost per call. The average cost per call, where I consider a cost to be an operation. Okay, so let's drill down into this and see specifically what I mean here. So first of all, every time I call append, I'm going to increment the call up front. All right, so that's that. And let me say that, okay, basically I do, we'll say one operation every time I call this method. This is kind of, I'll approximate it as one operation. Maybe you could say it's two, but I'll just say one for now. Kind of group these two things together. It's like I always do this one thing, this one chunk of things, no matter how many elements in the array. But sometimes I have to do a lot more. So when I call this double capacity method internally, this is not something that the user is aware of. We don't consider that to be a call from the user's perspective, but it's something that happens internally, and we have to do a lot of work. So every time that we assign an element to this new array, we'll consider that to be an operation. All right? So basically, yeah, I guess I'll focus in here on the array assignments. So I do an operation every time I assign something to an array. I'll consider that to be the work because I have to, I have to dereference a pointer, go to a location of memory, and then change the thing there. That's work. Usually I only have to do that once, but sometimes I got to copy everything over and do it a whole bunch of times. So the question is, all right, so I can get the amortized cost. So I'll just go ahead and make a method for that. So I'll just return self.operations over self.calls. So I'm just implementing the definition I had up here. And what I want to do now is actually plot. So I want to plot the amortized cost as I add more and more elements. So let's see, I'll go up to maybe like 200 or so. Yeah, actually, let me make that a variable. And what I'll do is I will keep track of the amortized cost that I've done up to this point. So let me say, okay, so amortize at index I is equal to mylist.get amortized. All right, so now what I'm interested in is, okay, let's say that I've added the first 10 elements. What was the amortized cost? What was the average cost per operation, what was the average cost per call of those first 10 calls? What was the average cost per call for the first 10 calls? What was the average cost per call for the first 11 calls? What was the average cost per call for the first 12 calls? And so on and so forth. So let me make a plot of this. So, let's see, I'll say np.a range 1 and elements plus 1. And I'll plot what I got. And so on the x-axis, I'm plotting number of calls I've done. And on the y-axis, I'm plotting the amortized cost per call up to that point. Okay, so here's the plot that we get. And it's quite interesting. So if we look at this, let me actually make it a little bit wider so we can hone in a little bit. All right, so, at first, I only do a single operation every time I call append, right? Because I just have to do that one array assignment. But when I run out of space, suddenly I have to do a lot more, and I shoot up here. Cost me a lot more. But then, okay, so I've doubled my capacity from 8 to 16. The next 8 operations are not going to be too bad. So actually, then this average starts to creep down again. All right, so we had that one expensive operation, but hey, we have some good days after that. But then suddenly we run up against capacity again. We got to double. And so then this shoots up. And then we double, and then it shoots up, and we double. So we keep seeing this pattern, but what's interesting is if I continue this, let's say I go all the way up to 2000. Okay, it seems like we have a ceiling, actually, that we never go above. So in particular, it seems like here the ceiling is 3. Okay? So what you could say is if I was trying to come up with the worst case, seems like on average, no matter where I am here, I could say, well, the worst case is never any worse than 3 operations. In other words, the worst case is actually a constant time here. So this is, for array doubling list scheme. This is the amortized cost for that. So it seems like we're upper bounded by 3. Now, another thing I could do, though, is I could say, well, maybe instead of doubling the capacity, maybe I'll triple the capacity. So maybe I'll have another method here that actually triples the capacity. And so just a very simple change here. And so let's see what kind of difference that makes. So if I were to run that code, and let's see, I want to keep this plot here, so maybe I'll just open it in another window for a second. So now we're going to do tripling. So what's interesting is it doesn't have to do it as often, right? So you see these bigger gaps between the expensive operation. And it also seems like the ceiling is a little bit lower. In fact, the ceiling here is 2.5 instead of 3. So we have a space-time trade-off. If we're okay having more unused space, so if we triple, we're not using 2/3 of the array when we start there. So we're saying, hey, if you got a little more memory, you can give me more room to grow, and it'll take less time. So that's a space-time trade-off there. Okay, I should point out that if we want to keep an upper bound that's a constant of the amortized cost per call, so here if I have the doubling scheme, it seems to be 3. I never do worse than 3 operations on average. If I want that to be a constant ceiling, it's very important that I increase the capacity in proportion to the current capacity. So here I'm saying double, right? And then I had the scheme where I did 3. That's another option. I could say, okay, but both of those are in proportion to the current capacity. If I instead were to ignore what the current capacity was and always do the same thing, so to add a constant here, so we'll say maybe C is equal to 10. So let's say that I'm just adding some constant each time, let's look at the difference. So now if I make the plot, unfortunately, we lose that ceiling that we had. The number of operations actually now increases as the number of elements in the array increases. So we actually now have a linear amortized cost. So the average cost per call for a method actually is going to take longer if I have more elements in the list, and that's not good. So we need this to grow in proportion to the number of elements that are already there, and then we can put a ceiling. So my question now is why the ceiling of 3 if I'm doubling? So I want to examine that mathematically. So suppose I am adding n elements. What's the formula for the number of operations? So it's like saying I've done n calls. Okay, give me a formula for the number of operations I've done, and then I can give you the amortized cost. So one thing I'll say, okay, so the easy part is I know no matter what, I'm always going to do this one operation to assign an element, right? So no matter what, I have to do n operations to assign the elements I'm adding. The harder part is analyzing what happens for all the doubles that'll do. So let's suppose that n is a power of 2, and we start off with a capacity of 1. So really here, I'm actually going to focus on the worst case. So what's the worst case formula for the number of operations? Because look, if I never have to double, then it's always 1, right? But I'm more interested in the case where it's like, okay, you just got up to 1024, now you're going to add 1025 elements, and suddenly you shoot up. So I'm going to look at that case. So if we start off with the capacity of 1, what we have to do to get up to n is we have to do 1 plus 2 plus 4 plus 8. Right? Every time we double, we do this number of operations, plus 16 plus blah, 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 all the way up to... so if we were exactly going to stop at n, it would be n over 2 operations. Because it was like, okay, you know, I didn't have to, you know, the last time I had to double it was n over 2, and now I'm exactly at capacity, so I don't have to double. But let me be a little more pessimistic and say, okay, I'm going to double you once more. Okay? And so I need to know what is this formula? So these are all the operations I have to do for doubling. So first I have the adding or the assignment operations, which have to happen no matter what. And then I have the doubling operations. So the question is, what is this formula? Okay, to see what this formula is, it's actually much easier to draw a picture. And when we have a doubling factor of 2, this is a geometric series, and it's an example specifically of something that we call Zeno's paradox. Okay, so let me tell you what I mean. So let me set up a little line here. I'll set up like a little rod or something. And I will consider this rod to be of length n. So let me do that. I'll say that, okay, this little rod here represents the number n. So now what I'm going to do is I'm going to take that rod and I'm going to create a copy where I have the width. Okay? So I'll put this here, and this is now n over 2. All right? And let me take that rod, have that, and put it right next to the n over 2. And so that's going to be n over 4. And let me take that n over 4 bit, have that, and put it there. Now that's n over 8. And what you'll see is, as I keep, you know, I can keep doing this as long as I want. I will never, so I'll zoom in here just to show you, I will never quite reach the end of the n rod here. So I'll take that one, I'll copy it, I'll have it. I'll take that one and I'll copy it and I'll have it. and so you'll never quite reach the end point here. So this is, you know, it's not really a paradox in the strict sense of a mathematical paradox, but it's just, to us humans, we don't really understand infinity very well. So it's strange to say that, well, if you were allowed to do this an infinite number of times, you would never quite reach the end. In the limit, you will reach the end of the rod, but you will never quite reach it. So actually what we can say is that this whole formula it's less than 2 times n, right? So I'll never exactly have twice that rod there. Okay? And so the implication for us here is that this part, so in the worst case where we just doubled, right? And so I'm being, you know, just slightly like sloppy at the end point here, because I'm saying, you know, if we were exactly at n operations and n was the power of 2, then we wouldn't have to double, but I'm saying, hey, let's just double one more time. So in the worst case where we actually do that, then this sum here, we can say, you know, it's less than 2n, right? And so therefore the total number of operations, which is going to be the assignment operations plus the doubling operations, which is n plus 2n, so the number of operations, it's actually less than or equal to, you know, never exceeds n plus 2n. And so if I look at the amortized cost, well, that's the number of operations. So that's n plus 2n over the total number of calls, which is n. Well, n plus 2n is 3n. Quantity over n is 3. So there's our magic number. Now to give you a more general formula, so I'll say here general formula for a factor of, we'll say d doubling, or factor of d capacity increase. So the general formula, it's a geometric series. You can look up the general formula for this, but I'm just going to state it here. So the doubling, or it's now the capacity increase. So we still have assignment operations as being n, but now the capacity increase, we can say, is less than 1 over 1 minus, should be 1 minus 1 over c. Okay. So here we had, you know, when c was 2, we had 1 over 1 minus a half, which is 2. If c is 3, we have 1 over 1 minus a third, which is actually 3 halves. So you see that gets smaller. This actually gets smaller as c gets larger here. So remember I told you when we tripled, I was able to bound this by 2.5. So that would be 1.5 plus the 1 operation that we have to do for an assignment. Just to show you that again, you know, if I change this number to a 3, then this is never going to go above 2.5. All right, so hey, we can come up with an exact formula that explains what's going on here. And so that is the amortized cost for the array list. Good. So we see it's a constant if we always increase in proportion to the number of elements that are currently there. So I'm just going to ask you a question real quick to make sure that you understood, you know, the space-time trade-off and the basics here. And then I'll continue on to one more thing, a little bit of theory about where we can break this a little bit if we add a pop operation, and how to fix it. Okay, as you can see, it's actually a little bit later in the day. I realized there's one more thing I wanted to say to give you just some intuition about what's really happening here. So I think I've explained properly why we have these different constant bounds when we scale the array in proportion when it runs out of capacity, and that if I'm scaling by a factor of 1.5, it's a space time trade-off where this constant's a little bit higher here, but I use less memory. I have less unused stuff. Whereas if I do by a factor of 2, the thing might only be half full at times. So I can go a little bit faster, but I have to use more memory. And then if I increase by 3 times, I go even faster, but I have to use even more memory. What I don't think I completely finished explaining is why this ends up being linear. So I showed a few different examples here if we add a constant amount. So if I have to increase my capacity every single time, or every other time, then I get this. If I have to increase my capacity every 10, I get this. And if I have to increase my capacity every 100, I get this. And so just to really bring this home here, what I'm saying is, if you're going to do something really expensive, like copy all the elements of the array that are currently there into a new array, you better not do that too often. So in other words, and you kind of see it happening here, if I'm going to give you a big ask, I better give you a big time to recover. And now I'm going to give you an even bigger ask, but I'm going to give you an even bigger time to recover. You see? And so here, I keep asking for bigger and bigger things, but I hardly give you any time to recover. So you sort of get this, it's like, I'm still trying to recover from the last one. You hit me with another one. I'm still trying to recover. You hit me with another one. And so it turns out you just scale up here, like that. Okay, so I wanted to show actually these 3 different constant examples where, again, we have some kind of similar trade-offs. Here, I use a constant amount of extra memory that's larger. I say, okay, I'm going to allow you to have up to 100 unused elements. But unfortunately, having the constant interval doesn't give us enough time to recover, because the amount of work that we have to do with these big asks is getting bigger and bigger. So we actually should be waiting longer and longer until we make the next ask. Okay, so that's the last thing I wanted to say to bring that home.